Hello, we're Team Cobra. I'm Victor Gutierrez. I'm a freshman, and I plan on majoring in course 2 mechanical engineering.
Hello everyone, I'm Pedro Polanco. I'm a freshman majoring in course 2 mechanical engineering.
Hi, I'm Emily Salvador. I'm a sophomore and I'm majoring in computational biology.
Hi, I'm Dana Wilmot. I'm a freshman here at MIT, and my intended major is course 9, which is brain and tog sci.
So, challenge. Our challenge was to mimic a realistic scenario of flying in an urban or whatever kind of environment and having to pick up the chemical and visual readings. So challenge 1, which was the obstacle course with the hoops, kind of simulated having to fly through places where you had to fit through tight spaces and not exactly where you're going. And challenge 2 was the visual, chemical, and wind components. And so you'll be able to go in somewhere and see things where people couldn't exactly see anything, and figure out what kind of chemicals are being exposed in that scenario. And now I'm going to pass on to Emily to talk about how we tackled this problem that we had.
So we wanted to come up with a really effective design strategy. So we wanted our quadcopter to be efficient. We also wanted it to be cost effective, and we wanted it to be really easy to use, that really anyone could use it. And some of the design components that we considered when going through this process was the Phantom, the GoPro camera, how to get communication between our computer and the quadcopter, and the chemiresistor. So for the Phantom, since it was a manufactured product, you'd imagine that it'd be the most efficient system that it could possibly be. And because of that, it was hard to hack into the robot to directly change anything. So for example, it would be hard to read the IR signals to create an autonomous system from your computer. You also need to have a degree of knowledge in control theory to be able to effectively maneuver the quadcopter using an autonomous system, because as you've seen in other teams' videos, it was very hard to, it had a lot of drifting around, so it was hard to keep it in one spot. Because of that, we thought that autonomy was really high risk, and if we were working for a company, we probably wouldn't take that avenue, so we decided to look into alternative ways to program our machine. Dana's going to talk about the GoPro.
Right, so we were given a GoPro by the OMA, which was super generous, thank you. And when we were hooking it up, we realized that the GoPro had a 3-second lag when connected with our computers to the live stream. So we looked for different options. We ended up going with the GoPro app downloaded on our smartphones, and we found that it only had a half-second lag, which was considerably better. So the GoPro worked 2 ways for us. Not only did it give us an image capturing technology, it also allowed us to work with the z-axis. So if the aerial view that we were given could give us the XY plane, we got the z plane from the camera. Emily's going to talk a little bit more later about the motor that the camera was attached to. So we really wanted to make sure that the GoPro was the most secure it could be. So we decided to build by hand a framework that would go underneath the quadcopter. We decided to use a lightweight plywood, and we carved out a sort of hook shape. And attached to that, maybe you can see, we attached a plastic wheel. So what would happen was that when we turned the camera with the motor attached, we would have free range, and the camera would roll along the wheel as well. We decided to make sure that the camera and the framework that we attached it to was ideally placed, so to counterbalance any torque. So we put it underneath quadcopter as close to the center as we could. Now I'm going to hand it off to Deja. Oh, sorry.
So as Dana mentioned, we used the camera to kind of give us a height of where we were in the course. But also with communications, we used Bluetooth to kind of send signals to the Arduino, and in the case of the servo. Originally when we were using the servo, we were thinking we were going to use a potentiometer to send an analog signal, and basically it'd be like a mini remote control, and you would turn it and then the camera would turn. But we actually decided to learn something new, and we used a program called processing to create a user interface on my computer. So you could actually scroll across the screen and have the motor turn wirelessly. The Bluetooth had a range of 10 meters, and it was also very cost effective. It was only $22, while most Wi-Fi serial links are around $80. And we also used it to transmit data back and forth from the chemi resistor. I just want to show you kind of how our user interface works. So we run processing, and then it will create a serial link with the Bluetooth chip, and when it turns blue, you could, I don't know, it's hard to see, it's small, but basically, as you scrolled across the screen, it would turn the motor. And Pedro is going to talk about the chemi resistor.
So we were, as you've heard many times, we were charged to be able to pop several balloons that had some unknown gases in them, detect those gases and identify them. So to pop the balloon, we simply used a pin, like many of the other teams have. And to detect the gases, we have used a chemi-resistive sensor. So in creating the chemi-resistive sensor, we use single-walled carbon nanotubes to trace out a small film on white paper. We tape the film onto a little piece of foam, and then wire that foam onto a power source and another resistor in series. So doing so created a voltage divider such that when the gases made contact with the chemi-resistive sensor, the voltage, the resistance would go up or down, and then the voltage red would increase proportionally. So we attached a wire in between the two resistors, attached to a Bluetooth analog readout, and then we used the Bluetooth serial link to send that information back to our computers, and then we could read the voltage. So if the voltage went up, it should be an oxidizing agent, so it would be index dependent. And if it went down, then it would be the reducing agent in chlorines. And since we also had to overcome the challenge of facing the issue that the wind from the propellers would blow any gas away, we decided to position the chemi resistor at the bottom where the needle was. That way, as soon as the balloon was popped, some gas would hit the chemi resistor and we would take a reading. And now I'm going to pass it on to Victor.
So this is our cost. This is everything that our individual design required to purchase. Most of it's a pretty simple battery, Bluetooth, which Emily mentioned was cost efficient as opposed to other options. One thing I want to mention is the Arduino. We chose the Uno because it was the lightest as well as the most cost effective, while also meeting our demands that we needed for the servo and the Bluetooth communications, things like that. Our total mass was 134 grams. This was important to take into account because we wanted a quadcopter that it wouldn't be too heavy if that was way below the max load that the quadcopter would carry. And that way we had the most increased endurance and range, and we wouldn't have to worry about being slowed down or running behind battery run out. Our total cost was $67, which was way below budget. And any corporation, it's important that we don't go over what we plan to spend in games. So now I'll turn over to Emily, to Dana, to discuss what we learned.
All right, so I think that we worked pretty well together as a group. We had a great synergy. We did learn a lot of skills, and both teamwork and technical skills. For example, we had to learn how to set realistic goals. So one of the things that we considered when starting this project was whether we were going to attempt autonomy or not. And we realized that given our time constraints and the skills that we had in our group, that it would not be feasible, so we chose not to. Another thing is time management. We definitely tried to do things in advance, and as we discussed it once when we were in the group, we never felt super pressed for time. We made sure to plan ahead and give ourselves some leeway. On the technical side, the OMI and the Momentum program were super great in giving us tutorials on what we needed to learn. For example, to create the chemi resistors, we had Joe give us a tutorial session on how to do that. And we also used the Arduino and software as well. I'm going to hand it over to Pedro.
Alright, so having gone through the whole flight competition, there are several issues that came up, and knowing what has happened, there are some things we would like to have done, or if we were to continue the project, some things we would like to do. One of those would be to improve the integrity of the design. So ideally, we wouldn't be using duct tape. We would be like probably soldering everything onto our quadcopter. Ideally, we wouldn't be using something like plywood. We would be using some molded plastic or something along those lines. Ideally, we would also have had more practice and more testing done beforehand to see the problems that came up earlier. And finally, we came up with some problems with our communication devices. So it would be nice to have a more reliable device than we have. So finally, we'd like to thank all our companies for listening, especially Jacob Laboratory who sponsored us. And we'd like to open the floor to any questions.
This is a simple question. Puts me in the position of Captain Hindsight, the last team, and to should avoid a question. Most of the teams spend a certain amount of time and effort finding ways to sharpen up needles that would pierce the balloon. What would have been wrong with, say, getting medical type needles, which are industrially manufactured in huge quantities, come in very often large diameters, they're extremely sharp, and will give you the advantage when the balloon pops with a needle, since the balloon by definition is under greater than atmospheric pressure, it's going to squirt some gas and maybe liquid right back through that needle at the sensor.
That's an excellent question. So we actually used a safety pin for our design, which was already sharpened, arguably. But that's a very good point. I think that most of the teams didn't think of that, and it would have been a really good way to capture the gas to look at after the fact.
Thanks again.
Thank you.